Sure, I am actually going to cover these standards right here, standards 9.4 to 0.1.1-2, which is going to focus on ecosystems and energy. And yeah, that's kind of it. It's almost like a mini ecology unit with some population dynamics thrown into it. So let's get to it here. So species, when they do interact, okay, there's a couple different ways that they can interact, or ways to describe that interaction. That can be positive, where both individuals benefit, and we call that a mutualism. So an example might be a sea anemone and a clownfish. Commensalism means that one species benefits and the other one is unaffected. So barnacles on whales would be an example, because the barnacle doesn't harm the whale, but it does give benefits to the barnacle, like new... like barnacles are sessile, they don't move, so now they basically have movement, they can travel, other barnacles can latch on and form their own colony there. And then benefits versus, or benefits and harms is parasitism. So one organism, benefits from it, like a tick on a dog, while the dog is harmed by that. Populations do grow, and there's two ways to describe that growth. You can call it exponential, the J-shaped curve, and then the other one is logistic, and that is the S-shaped curve. So with the exponential, conditions are perfect, lots of resources, and the population rate just takes off. With the logistic, it accelerates very quickly, okay? And then it's going to start to slow down because maybe resources start to be deplenished. And it's going to reach something called the carrying capacity. So it will peak past the capacity, and organisms will die because there's not enough resources. And then they'll dip below, and then we'll see an increase again. And so it kind of goes up and down over this carrying capacity. So they try to draw the line that best fits that up and down up here. So the maximum number of individuals of a particular species that the environment can normally and consistently support is that carrying capacity. So we talked about the St. Matthew Island reindeer, okay, how they had no predators, and their population skyrocketed, but then they ate up all the lichens, and then they had to eat the sedge grass, which wasn't, what they really preferred, and then, that eventually ran out, and mass starvation, all the reindeer basically got wiped out. So factors that can increase carrying capacity: environmental factors like food or climate, just conditions that advance the population. This gets a little bit more technical, but technological efficiency. Like if you think about the human race, our population capacity is increasing based on technological advances, as well as like behavior. But there's comes the question as to like how big is Earth's carrying capacity for Homo sapiens, and then maybe a decrease in body size and resource demand. That would also increase carrying capacity. Factors that decrease carrying capacity: a change in the climate. So yes, both of these on both sides of that arrow, because if it's detrimental to the organism, then you're going to see the population go down. Okay, environmental degradation, things just not working right, pollution, just the energy flow in that ecosystem, depletion of non-renewable resources, extinction of a bioresource, or maybe a new competitor comes in and there's no predator for that new competitor, so it outcompetes everybody. Okay. This is a diagram showing how populations peak past the carrying capacity, and then there's a sharp decline. And then if it's an extreme decline, the population could die out, or give it enough time, it will come back and teeter, or if it's damaged, maybe the carrier capacity is now going to be permanently lowered. So you can kind of think of it as like putting water into a bucket as annual reproduction, but there are factors that will decrease that population, like old age, loss of habitat, human development, weather, starvation, accidents, predators, and hunting, disease, and parasites. So ecosystems can be changed by natural processes like lightning, floods, hurricanes, volcanic eruptions, drought, extended cold periods. Okay, natural processes can change the ecosystem, as well as human activity, habitat destruction. Okay, habitat fragmentation, taking a big chunk of land and subdividing it and developing certain sections of it. When you cut habitats, you're decreasing their area, and also breaking it up, so it's really dangerous for them maybe to like cross that road. If you take a section of land and build a road right in the middle of it. Overuse of resources, pollution, and introducing species, okay, invasive species. So when we introduce species, they are in a new habitat and they may not have a predator to keep their population in check. So they will grow and reproduce quickly, and they can thrive, in many habitats. No diseases, no predators, no pests. So it becomes very difficult to remove or control them. And why are introduced species problems? Well, they can destroy ecosystems. They can mess up the balance. They can change the food web. Okay? They can reduce biodiversity or even degrade habitats or transmit exotic diseases and parasites, and they can cost the economy money if they are dangerous to that ecosystem. So like if there was a parasite that really affected fish and wiped out the fish population, okay, well, we eat fish, for a food source, so it could cost you an economy. Or maybe there's a new virus affecting plants, okay, or fungi like blight, and it's introduced to a new area and crops are affected, and now we're in trouble, okay? So examples of introduced species: killer bees, kudzu in the United States, which is this fast-growing plant, and it grows very rapidly. I think it grows faster than bamboo, and it just can cover vehicles, cars, and houses in just a matter of days. Cane toads of Australia. You guys watched a documentary on that. Gray squirrels of the UK. How gray squirrels were all competing with red squirrels. Burmese pythons in the United States. How people kept them as pets, and then when they got too big to take care for, they just couldn't take care of them anymore. They released them in the wild, and now Burmese pythons, they're out in the wild. And in our very own home state, Minnesota, zebra mussels. Okay, so I'm going to talk a little bit about zebra mussels. So here you can see the map of zebra mussels. And what they do is they alter the habitat by removing the algae. Okay, so here is the sun, and aquatic plants spread to the deeper water. And now our water clarity is going to dramatically increase. Sunlight's going to penetrate deeper. The water column is going to warm to greater depths. And you don't really need to know those two things. But zebra mussels remove algae from the water column, and their waste gets deposited on the lake bottom. You can see that here. And some of that nutrients will mix back into the water, and some nutrients will be consumed by other benthic organisms. But the net movement of energy is from the water column to the bottom of the lake. And when you have less algae, there's less food and oxygen for the fish. Okay, so I'm going to talk a little bit about food chains and webs, trophic levels, and how energy is transferred. And then I'm done with this little lecture. But I also want to talk a little bit about birth rate, death rate, immigration, and emigration. So remember that these are 4 factors that can change populations, and 2 factors increase: birth rate and immigration, individuals moving into that population. And 2 factors can decrease: death rates and emigration. They exit, they leave. So here's a food chain. Okay. And energy is shown by the transfer of the arrow, and the arrow points to who gets that energy. So we have grass. It's always kind of your first trophic level. It's a primary producer. They're the only ones that can convert sun into chemical energy that we can use. So the grass gets eaten by a grasshopper. We call the grasshopper a primary consumer because they're the first to eat the producer. And then a frog may eat the grasshopper. So now this is secondary consumer. Okay. And then if a snake eats the frog, it could be a tertiary. And a hawk eats the snake. Apex just means top predator. But eventually everything dies. And then you have your decomposers that will return nutrients. Here's another. This is a food web showing multiple food chains interconnected to each other. But it usually starts off with grasses. So grass to rabbit, primary consumer, rabbit to hawk would be secondary consumer. Okay. Yeah, but starts with a primary producer, and then you have your primary consumers and your secondary consumers. Okay. This is an energy pyramid showing that most of the energy comes from our primary producers, and then when energy is transferred, there's this rule of like 10%. Now, I'm not exactly sure if that's true, but most of our biology textbooks, however, emphasize this 10% transfer. So 10% of 100 is 10, 10% of, oh my god, 10% of 10% is 1%, thank you. And then 10% of 1% is 0.1. So as energy is transferred, there's less available. Okay, energy gets lost as heat and waste products, and that's why it's only 10%. But remember, everything will eventually die and decompose and recycle the nutrients back for primary producers to use. And that is it.